So where we were looking at stakeholders and objectives. Specifically, we were in the subgroup of methods for multi-objective ranking. And in this group, we have looked into multitask learning. We have looked into scalarization. With multitask learning, we can predict multiple things at once. With scalarization, we have the ability to combine things. And this could be either an average or OWA style, more guided mathematical forms of richer notions of averaging. So I want to quickly jump to the discussion next, which is around multi-objective multitask learning. So far we have seen that in multitask learning, we do have the notion of losses, which we have to combine. And essentially the problem then becomes like, can we treat multitask learning as a multi-objective optimization problem and then address this? So if we take a step back and look at the multitask learning formulation, essentially what we have is we have a number of functions which you have to learn, which has some shared parameters. So theta sh are the network parameters shared between tasks, and the theta t are the task-specific parameters. So essentially, if we have t number of tasks, then we'll have one set of shared parameters and t set of task-specific parameters. So here, the goal is to minimize some sum of losses coming in from each of these tasks. So if we have t tasks, then essentially we'll have t of these lambda scores, and which is going to weigh the losses appropriately. So here, the question then becomes like, how do we decide what the lambda t should be? Because if you give more weight to one task, then you might overshadow the other task and so on. So the problem this paper formulates into is the lambda t balancing problem. So the intuition, okay, again, let's look at the figure on the left. So we have the loss. The task 1 loss is weighted by lambda 1, task 2 loss is weighted by lambda 2, and so on. And essentially, we have the gradients being balanced using these weights as well. So now if you look at the figure on the right, and if you look at this intuition that if the gradient magnitudes are smaller, then perhaps we are very close to the optima, at least some optima for the task 1. So here, we would want the lambda 1 should be increased so as to preserve the local minima. Oh yeah, so this is not lambda square, this is lambda 1 and lambda 2. So we have t task, lambda 1, lambda 2, lambda 3, lambda 2, 4, and so on. So lambda 1 corresponds to task, the weight we assign to the loss of task 1, and lambda 2 refers to the weight we assign to the task, to the loss coming from task 2, essentially. So here, like, we want to say that I'm going to combine my losses using some weights, and these weights are lambda 1 and lambda 2, and so on. And if I see that one of my task gradients are small, then I should increase the weight because then I preserve the local minima. Otherwise, like, things might just run away from the local minima currently. And if the gradient magnitudes are very, very large, then we don't want to screw the other task. So lambda 2 should be decreased. So the weights attached to a task which has higher gradients, we should perhaps decrease it. Otherwise, this task is going to overshadow everybody else, and then we're going to lose the learning we've had so far. So you see that we start to face some of these problems that, okay, I need not have the same lambda at the start, and maybe we want to change lambda based on the gradients we are observing. And if you're interested, there's this very nice blog post which is linked at the bottom of the slide, which you should see. Yeah. So this blog post talks about multitask learning in general, but also like presents some very nice, easy to use code for some of these like multi-objective problems as well. So I highly recommend looking at it. Yeah, so essentially what this NewLift's 2018 paper says is like that instead of optimizing the summation objective, we want to consider multitask learning problem from the lens of multi-objective optimization. So here, we're kind of optimizing a collection of possibly conflicting objectives. So far, based on the examples and case studies we have seen so far, and the correlation plots we have seen so far, we know that oftentimes some of these objectives are conflicting. So how do we optimize multitask learning in a multi-objective fashion? So essentially, what we do is like we cast the multitask learning objective as a vector valued loss. So we have loss coming in from each of the t tasks we have, and this is a vector valued loss. And then what we could do is we could use, so the authors use KDD conditions some standard like reduction operations to find the common descent direction of shared parameters for all objectives, which is necessary for optimality. So essentially, when you look at this problem and you have a vector valued task, vector valued loss, okay, vector valued loss coming in from the t task you have. So essentially what we could do then is we could apply KDD conditions on it and then find a direction of the descent, which would kind of decrease the solution loss for at least some of your tasks. And this is essentially doing it not independent of the other task, but then you're now treating your different task as a multi-objective problem itself. So in general, the solution which is satisfied is this is Pareto stationary, but it's not necessarily Pareto optimal. And we want Pareto optimal solutions. So essentially, if you look at this problem, which is some minimization of some of your loss parameters for t task, and you're summing the loss spaces based on the individual t alpha values, and each loss is coming from a specific task. The minimum, when you solve this problem, then the solution, if the solution is 0, then you have a Pareto stationary solution. And if it's 0, then at least it gives you a direction, which improves all different objectives. So now this is the key aspect over here, that either you will end up in a Pareto stationary solution, or you end up in a solution which gives you a descent direction, which improves all your objectives. So now you're slowly getting towards a Pareto optimal front. And this is mathematically equivalent to finding a min norm, like minimum norm solution, in the convex hull of the set of all solutions. So essentially you have t task, and the t task you have will span t solutions. And essentially the mathematical equivalent of finding the solution for this problem above is finding the min norm solution in the convex hull. And now this problem is easily solvable. So we have like, in the optimization world, we have Frank-Volz solvers, which are literally can be used very easily to solve some of these problems. So essentially like solving a min norm in a convex hull set of solutions is doable in a Frank-Volz solution. So which could be employed over here. So there's a question. So moving from a loss of sum of task to a generic loss for the entire task creator. Yes. So Sergey said a very nice formulation of this, that yeah, we're not looking at summing the task losses, but then we're trying to find out what weights we should give based on the direction which improves all these tasks together. So essentially, so far in the multitask learning, we had pre-specified some weights that, okay, I have 3 tasks I want to optimize, I want to predict in my model. I'm going to assign it weights W1, W2, W3. Now, that does not guarantee Pareto optimal solution for the 3 tasks. Instead, if we formulate this problem as is done here, and then use the KDD condition formulation, then we are guaranteed that at least we get a descent direction which improves all the different tasks together. So here, essentially, this is a nice catch over here, that when you view your multitask learning problem as a multi-objective problem, then the Frank-Volz solution here gives us a Pareto optimal solution for some of your multitask problems. And they have some nice evaluations and radar charts to plot that you're indeed performing like much better, like the losses for each of your tasks. So if you look at the green plot over here, then the corresponding losses are lower for all of these tasks together. So again, like taking a step back, so far we have said that, hey, we want to predict multiple things. So then we have some multitask solutions. We want to combine multiple things. If we have made multiple predictions, then we can combine it using averaging or like OWA style averaging. And we've recently just looked at multi-objective formulation of multitask learning as a solution. So now I want to like go a bit slightly different and talk about like making predictions real time and combining things real time together. So here, what we talk about is a bandit-based solution. So this is a multi-objective bandit solution. So I'm just going to spend 2-3 minutes laying the background of bandits and contextual bandits for people who don't have the intuition about these, and then quickly go on to a multi-objective contextual bandit solution. So in the multi-objective contextual bandit, like let's say we pick up a multi-arm bandit problem. So we enter the world with 0 knowledge. We pick an action based on some action policy pi, and we observe some reward, right? And ideally, we want to maximize the reward or minimize the regret we have. And in general, the question then becomes like, how do we choose a policy which minimizes the regret? If you look at contextual bandits, then contextual bandits problem have just one difference. So we also observe a context. So now when we are picking actions, we are picking actions conditioned on the context. So why is context important? So if you look at this homepage of Spotify, so on Spotify, we do care about looking at what the time of the day is, what user there is, what's the user's historic interactions with some of the playlist been. So these are all important contextual signals which we should consider and look at when we try to make these decisions. So that's why like a contextual bandit formulation is a lot better solution for us. So again, just a quick difference, like the only difference between a traditional bandit and a contextual bandit is that we additionally observe a context. So again, like I'm pretty sure a lot of you are familiar with these formulations, but then if you aren't, then that's a brief overview. That we ideally have to decide an action selection policy. We pick an action and then we show content based on that action, and then we observe some reward. So a lot of recent work has extended some of these like contextual bandit models to a multi-objective scenario. And bandits have a very nice property because these are like online. They help us do this explore exploit trade-offs pretty nicely. So there's some recent work around extending them to multi-objective sense. So the first paper by Robert Busa, who was at Yahoo at that point of time, I think he's at Google Research now. So they have done some work on multi-objective bandits, not a contextual bandit formulation. There is some work coming in from Turkey around multi-objective bandits with some dominant objectives. And we have a paper at KDD this year on multi-objective contextual bandits. So I'm going to give a run through of the approach which we have in the KDD paper this year. So we're going to talk about this in the coming week as well. So just keep an eye out for that. So let me take you back to where we were in the world of multiple stakeholders, multiple objectives. So we know that we wanted to optimize a multi-objective function, and that function has inputs coming in from the different stakeholders we have. So in this paper, which is, as I mentioned, a KDD 2020 paper, we propose like joint optimization using a multi-objective contextual bandit model. So essentially, the function f we were talking about here, like which considers multiple objectives together, what we formulate is we say that, okay, we should use a generalized Gini index formulation to combine some of these objectives. So the Gini function is a very special form of ordered weighted averaging. So I briefly mentioned about OWA before. So OWA is an ordered weighted average. So it's a mathematically richer form of averaging, wherein you are ordering your scores and then deciding the weights in real time, and then kind of averaging using those weights. So essentially, if you use a very specific formulation of OWA, which is the generalized Gini formulation, then it kind of gives you the benefit of preserving impartiality with respect to the individual criteria. So in a sense, it kind of a Gini formulation of combination. So Gini is just a scalarization function, right? I mean, so far we have looked at scalarization like W1S1 plus W2S2, or a weighted sum, an average, and a Gini index formulation is another specific form of scalarization. But it has some specific properties. The specific, very important property is that it prefers allocations that are more equitable. So essentially, what happens here is, because this is an ordered weighted average, so the order of the score. So let's say I have 3 objectives, and we real time decide how we are doing on each of these 3 objectives. And then based on that, we order. So the things which are really bad, let's say we sort in a decreasing or increasing order. So if we sort in an increasing order, they come up at the top. And now I know that the topmost sorted element is the worst performing one, and then I'm going to give it a high weight. So there is a dynamic weight allotment going on over here. And based on that, you see how you're performing in real time, and then sort it based on the ordered weighted average, and then kind of gives you a weight. So essentially doing that, we try to control that. We prefer allocations that are more equitable, because if some of your tasks are suffering, some of your objectives are suffering, they get a higher weight in the next round. So let's just look at like what would a contextual bandit solution around this Gini formulation look like. So the goal is to find an arm selection strategy. So this is typical of any contextual bandit formulation, right? That we have some arms. So arms are playlist for us. So in general, if you go to Spotify, you have a bunch of playlists. Let's say for each user, we select a bunch of 1,000 candidate playlists. So each playlist is a card, and which is an action. So I mean, which is an arm you select. So if I pick up a if I select an arm, then that arm corresponds to us showing that playlist to the user. So ideally, finally, we want to learn an arm selection strategy. So give me a property distribution based on which I can select some cards in some playlist. And for each bandit instance at round T, we are given a set of features. So this is the context features. So what we are doing is we're saying that I'm going to contextualize, have some context encoded about like user music preferences, time of day of week, and so on and so forth. So these are real-time context which goes into our models. And then again, like if we had chosen an arm K, we assume that we observe a linear reward. So this is an assumption wherein we say that, okay, my rewards will, the reward I obtain will like decompose linearly based on the features which we have. So again, if we make the assumption that had this not been a bandit setting and had we known the feedback for each arm, then what we could have done is we could have easily done a full sweep, parameter sweep, and then picked up the best arm, right? The problem is this is a bandit problem, that we don't know what the true feedback, true reward for each arm would be. There might be a playlist which the user has not streamed at all, but then the user might love that playlist. So we don't know what the true reward for that particular arm could be. So that's one. Had we known it, then it could have been a very easy problem. Like we do full parameter sweep and then pick up the best and show it to the user. But it's not the case. The other interesting problem here is the vectorial feedback. So here the problem is the problem is that we don't have a single reward, right? I mean, in a single contextual bandit model, we just have one reward because we care about one objective. But here we have a vectorial reward. So this is another mathematical interesting property that now if we deal with like 5 objectives, we'll have 5 rewards. So now we have a vector of rewards. So essentially, because the feedback for each card, each playlist, each arm is not known to us, it is context dependent. So now we have to do some optimization and kind of select some policy which optimizes this function of Gini formulation. So here, if you notice, then this GW is the same Gini function which I mentioned before. So we have T task, we have K arms, we have T task, T objectives, and now what we're trying to do is like we're trying to maximize. We're trying to select an arm based on this maximization function. So just quickly going through some of the exact algorithmic steps. So we define the problem space. K is the number of arms. Number of arms is the number of playlists we have. D is the number of objectives. So this is a multi-objective problem. So we have D objectives, and we also do some parameter initialization for the ridge regression. I want you to remember that we have made the assumption that the rewards are linear. So that's why we could use some of these like linear prediction models, like ridge regression, to kind of infer some parameters during real time. So what we do next is we initialize the parameters, say that, okay, I'm going to assume a uniform strategy. All cards, all arms are equally probable. And then we kind of assign some auxiliary matrices for the ridge regression. So with these parameters set, what we say is we look at a session, the user comes into the playlist, the user comes to Spotify homepage, we observe some K features. So these are the context features which we are inferring real time. And then for each of those, we estimate what the mean reward could be. So we're trying to predict here what the reward would be based on what we've learned from the users and historic interaction so far. So again, we could do that by using a L2 regularized E-square ridge regression. Again, you can try other approaches, but we use ridge regression so that we get some nice parameter bounds for like lower bound on the regrade. So essentially, once you have the mean rewards, then what we can do is like we can show that user that content and do some online gradient descent. We get some arm probabilities, which we project back onto the set of arms A. Then again, we sample the arm, and then we observe the reward from the user. Once we have observed the reward from the user, we can go back and update the models, update the model parameters. So essentially, this is what's going on. Like we start with a uniform probability distribution to sample, arms from, we observe some features. These are the context features. We make predictions on what the typical, for each of the objectives. We're not just predicting one reward, we're predicting rewards for each of the D different objectives we have. Using that, we sample an arm and then observe a reward. And then based on how well we did, we go back and update the model. So in general, what this does is, this is doing two things at once, right? I mean, it's saying that, hey, I mean, in a bandit setting, in a contextual bandit setting, wherein we want to do this explore exploit property that I may not know what users might like. So I want to make sure that I keep on exploring some bit. So that's the property which this solution retains. And it does that while keeping in mind that we have a multi-objective problem at hand. So we're not just caring about one, but we are caring about the objectives. Pranab has a question around, assuming we are learning the weights, why is it important to order the weights? Yeah, so a very important question, right? So why is it ordering important? So assume, okay, let's take a hypothetical example. So let's say if I have 3 tasks, and for each of the 3 tasks, I have my losses. So loss 1 is 0.1, loss 2 is 0.4, loss 3 is 0.9. And let's say these are all normalized to 0 and 1 for easiness. Now I know that task 3 is like, I'm really doing very bad because my losses are huge. So just to get a sense of how I am doing on each of these, and I will assign the highest weight to the task which is doing worst at that point of time. So let's say I say that W1 is gonna be the weight I attach to the worst performing task in my current round. Now, how do I know which is a worst performing task? If I sort based on a decreasing order of the loss, right? If I sort based on decreasing order of loss, then whichever task is performing worse will come in at the first. And W1 is the weight assigned to the task which is performing worse. So now it kind of matches pretty well. So that's why, like, the sorting operator in the OW approach, it brings you the worst performing at the top, and then you assign a weight to the top. So you're not assigning a weight to a task, you're assigning a weight to the most important task at this stage. So there's a difference. When you do a weighted sum, you're assigning a weight to the task that, hey, I mean, I'm going to give a 0.7 weight to task 2, 0.1 weight to task 1, and you fix that. But here we are not assigning weights directly to task. Here we are assigning weights to the task which are currently important in my real-time process. Hopefully that convinced. Well, that's kind of explanation enough. The other question from Howley is like, how many arms do you have? If the action space is large, how does the performance look like? Yeah, this is a very, very important thing. So we have some simulation, good question. We have some simulation results wherein we varied the number of arms to a few thousand and 10,000s. And we kind of benchmarked on the real-time performance of the model. We also, in the actual test at Spotify, like we have a candidate selection stage first. So, I mean, at any given point of time, you're dealing with a few thousand playlists. You're not looking at the millions of playlists. So, I mean, this kind of assumes that you have a first stage candidate selection in place. Are arms independent? If not, does it impact parameter updates in terms? Good question. So we consider arms as independent of each other. This just kind of works nicely with the theory. Ideally, the arms are, again, like, so here you bring this a very important question into picture. So if we view the homepage construction, right? I mean, we are picking playlists and creating a homepage. So if you view the homepage construction as a whole page optimization problem, then you have to understand, okay, I've shown these 3 playlists. Now, what is the 4th one should I show? So this should ideally consider what you've done so far. But essentially here we are viewing each playlist as separate. So we pick a playlist and then add it to your homepage. So we are not doing a structured prediction problem. We're doing it independently. Have you considered doing exploration in the candidate generation stage? That's a good question. So in the candidate generation stage, so the candidate generation is a separate model in itself. And to be honest, like I do not know if we have done that for that particular problem specifically, but I do know that recently we've been working on not the homepage, but then like on the radio side. And then for the radio tracks, we have considered like adding fetching up a bunch more tracks from which are not just like exploitative, but also exploratory. And this is a very good point, which Hari mentioned, that we want to do exploration in the candidate generation phase. Why? Because it's not just the user we care about. We also care about the other stakeholders, right? So if you're doing your exploitation only based on the user objectives, then you're not exploiting your data enough. Because maybe you just pick up the moment you do a candidate fetching, maybe you've upper bounded the results you could have had on your other objectives. So maybe there is no tail supplier in your fetch candidates, and no matter what you do, you're going to tank your diversity metric. So that's why it's very important to pay more respect to the candidate generation phase, and in specifically these multi-stakeholder problems. The arms are different. So the arms are different cards. So essentially the objectives are, so we have D objectives and we have K arms. So when you, in a bandit setting, you pick up an arm. So when you pick up an arm, that means like I have a bunch of playlists and I decide which playlist should I show to the user. So what are some examples of the task? Yeah, so the examples, I'm going to quickly come back to some of these results in a bit, but some of these tasks are the heat map of correlations which I showed you, like the maximizing the click-through rate, maximizing the number of songs played, maximizing stream time, discovery, gender diversity, and so on. So the heat map are the exact same objectives we considered. How do you ensure the objectives of candidate generation are aligned with that? Yeah, that's a very good point. Again, like I think this entire discussion on the role which candidate generation plays in a multi-stakeholder problem, that's a very, very important point. To be honest, like we haven't explored enough on are you already bounding it by just fetching like some stupid candidates which won't ever improve some of your other metrics. So it's an important problem. I think like we should view, this is an opinion, an unsubstantiated opinion, I'll put a disclaimer, that ideally we should view candidate generation as importantly, at least in a multi-stakeholder problem, as like your ranking. Because again, like the bandit model needs a bandwidth to work with, right? I mean, if you're limiting its wings by just fetching the most relevant candidates and not candidates which might do well on some of the other objectives, then by default you're gonna like upper bound the performance you can have on some of your other objectives. So just to reiterate the point Hari mentioned, that it's even more important to kind of pay good attention to how we are doing in terms of our candidate generation in a multi-stakeholder setting. Okay, quickly going on. So I also want to ensure that we are almost in phase 3 of the tutorial, and we have to go to other phases as well. So I'm gonna give a bird's eye view of some of the multi-objective RL work which has gone into some recent research. Okay, so in a multi-objective RL setting, like, I mean, there are two primary strategies. One is the scalarize approach. So we have looked at scalarization, which is just a fancy term for averaging, right? So we can do average, we can do some OWA style average or so on. So here the goal is to find a single policy that optimizes a combination of reward. So which reward combination is preferred at which state? Because in a reinforcement learning setting, you're doing things on a state-by-state basis. And so there's a temporal aspect to your reward summations as well. And then the Pareto approach, which is like, can we find multiple policies that cover the entire Pareto front? So essentially, maybe it's not just one policy, but a combination of policies which give me the nice trade-offs which I might need as a product owner. So there's a nice tutorial, a bit dated, like 5 years old, on multi-objective reinforcement learning on some of these IEEE transactions paper. And they have divided the categorization into single policy approach and multi-policy approach. So again, I mentioned before that we can view it as learning a single policy, or I want to learn multiple policies which cover the Pareto front. So in the single policy world, some of the easier things to do is just consider a weighted sum of Q values. So what we can do is like we can have a linear weighted sum of Q values, which can be used as the synthetic objective function. Then, I mean, there are other approaches which are a bit more nice.
哦，我在坐在那个瑜伽球上，然后后面是我原来的椅子，是因为我上周腰突然间不舒服，
Somebody is unmuted. Can you mute yourself? Okay, I can hear some noises. If you don't mind muting, thank you. Right. So in the W learning approach, the problem is, the basic principle is that each objective has its own recommendation. So let's say that we have 3 different objectives, and each objective will say that, hey, I think this playlist is my preferred way of recommendation, and the other objective will say that this other playlist is my preferred way. And essentially, the final decision is based on the objective which has the highest value. That's okay. Thank you. So in general, in the W learning approach, essentially what's happening is that each objective picks up a candidate to recommend, and then the final decision is made by the objective which has the largest value. The other one is like a ranking approach. Again, very intuitive, very simple. What if we define an ordering of rewards? So in the ordering of rewards, we can say that, hey, I really care about the user satisfaction-centric rewards, so I'm going to order it higher. And then I really care about some platform rewards, so I'm going to order it lower, right? So then what we can do is we can use this ordering of rewards and check low priority rewards only if a decision is not possible by high priority rewards. So again, fairly simple to approach and implement. But the problem is, like, here you have to specify an ordering, and then you have to make sure that, like, you, even despite the ordering, you do kind of bring some of your other objectives up. A quick follow through on some of some recent, not so recent work around other multi-objective reinforcement approaches. So one is, let's we divide the problem into multi-phases. So the easiest thing I could do is, let's try to find a solution by considering only a single objective. So I have multiple objectives, I disregard them, I just pick one and then go to that Pareto front closest to me. And then what I can do is, like, now I can do from that local position, we can do some improvement, that we can move the solution towards one objective at a time. So we pick an objective, we go to the Pareto frontier by maximizing that single objective, and then we move around locally. So in that movement, we might end up going outside the Pareto front, and then we can do a correction and come back to the point on the Pareto frontier front as well. So again, it's very nice and intuitive to do in an n-dimensional space, that I pick up an objective, maximize that will definitely lead me to one point on the Pareto front, and then I can do movement one objective at a time. And the moment I step out, I can do a correction and come back onto the Pareto front here again. So these are some of the approaches. I want to highlight a couple of recent work, especially this work on dynamic weights in deep reinforcement learning. It's an ICML 2019 paper. So here, as I mentioned in the contextual bandit formulation, talked about before, that sometimes the importance of objectives changes over time, and specifically in an RL world wherein you have like states and there's transitions happening across states as well, then we don't want to fix the Ws, the weights. So this paper at ICML, Dynamic Weights in Multi-Objective Deep Reinforcement Learning, addresses this problem. It's a very nicely written paper. So here, I'm going to give a slight intuition about how the solution works. So the proposed solution is a multi-objective queue network. So here, the outputs are conditioned on the relative importance of objectives. So we have a bunch of objectives. We know, we compute the relative importance dynamically, and then this is what the outputs are conditioned on. So essentially, what happens is the weights change across states. So again, like based on the states, the importance of the relative objectives could change. And in general, this can become problematic because we don't want to jump a state and then suddenly forget everything we have learned about the objectives so far. So we want to maintain previously learned policies as well, because otherwise, like across each state, the problem of policy learning becomes intractable because you're not able to reuse learnings from the previous state. So this is why what the authors proposed was a two-loss combination. So essentially, to make sure that we are maintaining the previously learned policies from the previous state, even at the same time adapting that the weights are changing across states, what we can do is like we can have a loss on the active weight vector and the loss on the sampled weight vector, and like from the previous. So essentially, you have an active state. So what's my loss based on the weights in the current state? And then I can sample one of the previous states and then get a loss based on the sampled weight vector from the previous set. And then we can combine these two. So essentially what it's doing is like, it's respecting the current state and saying that, hey, I'm going to allow you to change some of the weights for your current state. But at the same time, I'm going to pick up some of these previous states and make sure that you don't like go and screw that policy up, so that you're going well on those things as well. So essentially, like one of the other things which they did was hot start learning. Like for each W, we can copy the policy based on the previous state and then do that. So essentially, what this enables us to do is like it enables the RL agent to quickly perform well for objectives that are important at the moment. So this is like the ability to change weights over states gives us this property, but this loss function here makes sure that we're not kind of having catastrophic forgetting across states in the weights, in the dynamic weights world. Okay, cool. So by no means this is supposed to be an exhaustive coverage of the kind of things that have been done in the reinforcement learning community. So a bunch of very nice references for that. So one is the multi-objective planning and learning, AMAS tutorial in 2018. There's some very nice lecture slides from the course at Edinburgh, which is talking about multi-objective RL. There's a nice survey, which is a bit dated, and then a couple of other surveys around that topic. Okay, so far, there were a few questions around how are these performing, what kind of approaches have we used, what kind of objectives we have used for the contextual bandit setting and so on. So let me kind of summarize some of these by looking at some results. So here, let's just start by first investigating the single versus multi-objective problem. So let's say that in the music context case, let's say that all we care about is like user-centric objectives. So this is a multi-objective problem, but it is still a single stakeholder, like we only care about the user. So in this world, what we see is like when we try out a single objective solution versus the multi-objective reinforcement learning solutions, then we find that the multi-objective model performs like much better than the single objective models. And this is not just true for one objective, but also true for all the objectives we consider. So this is interesting that if I care about clicks, then I should not only optimize for clicks, but I should optimize for total length stream, for total songs played, and so on. So why would that be happening? So one of the intuitions, we're still investigating what's going on in here, but one of the hypotheses is that because these are satisfaction tasks, and we know and we know that so in the satisfaction task, we know that from the correlation analysis that some of these tasks help each other out. So essentially what's happening is that because the satisfaction tasks are related, they will give us like help each other out essentially. There's a very nice Rex's 2018 paper on chaining of metrics as well. So if you look at some of these metrics, then essentially what happens is that I mean, a click has to happen for a stream to happen, right? I mean, you have to click a playlist and then only you can stream it. You have to stream some songs, then only you can stream like 5 different songs. So there is a chaining effect across some of these metrics. So that chaining effect, you should read that paper from Gillian McCauley from UCSD around chaining effect across these metrics. I think that could also help. And like, it also might have a regularization effect, as I think like somebody mentioned on chat as well. But again, like very exciting empirical findings, which we should understand that maybe there is some structure between these objectives, which might help some of your models learn better. So again, the takeaway being that optimizing for multiple interaction metrics perform better for each metric than directly optimizing for that metric itself. So now, I mean, the sum is greater than the parts essentially, right? So what if we add a competing objective here? So if we add a business objective, let's say gender exposure. So let's say we pick up a subset of artists and we want to expose them more, then we see that some of these results indicate that we can get significant gains in the business objective without hurting user satisfaction metrics. Now, this is a very important point. I think like if you're a product owner and if you have to take away one thing from the tutorial, I think it should be this, that it need not be a zero-sum game, right? I mean, when we try to optimize some business objectives, maybe we can get gains without losing user-centric objectives. So this is important because again, here we are talking about, it's not a trade-off. I mean, so far I've been using the word trade-off. That maybe you gain in satisfaction, gain in relevance, loss in diversity, loss in fairness. But here we are starting to see that maybe there are some cases wherein increasing the overall pie is possible as well. And if you increase the pie, then that means you can get gains for each of the stakeholders without somebody getting hurt in their metrics. And again, like just the way of doing multiple objective matters. So this is not to say that no matter how you try a multi-objective model, it's going to work. No, I mean, there are specific formulations which are going to be more useful than others. I'm going to take a couple of quick questions. So there's a question from Sergey on, does it matter if these objectives correlate in a positive and negative way? Yeah, so this will help, but then even if it does not, even if they're negatively correlated, then I think like it's the model's choice and responsibility to make sure that that we do well on competing objectives as well. So in the paper, we do have experiments around competing objectives, and that shows that, hey, I mean, gains are possible, but there you're kind of trading off some of these losses. So the other question is from Sumit, which is, what would be an example of reward for diversity of items being recommended? That's a good question. So let's say, I mean, the stupidest formulation could be how many sessions were diverse enough, or if you want to pick up, let's say, what percentage of your playlist has artists from lower popularity, right? So you can kind of formulate some of these quick and dirty reward functions for diversity. But again, very importantly, it brings to question, do you care about a session-specific diversity, or do you care about global diversity? Now, this is an important problem because I might just as well say that, hey, I just want to do good on this session and then just do and surface recommendations which are diverse in my current local session. But I also might want to say that, no, I care less about individual sessions, but I care more about global. So this month or this quarter, I want to ensure that I'm surfacing enough retailers. If I'm Amazon, then I want to surface tail retailers as well. So, I mean, then your rewards are delayed because you don't have a reward immediately available for your session. You have a reward after some sessions have happened on a global level. So oftentimes this kind of throws up this very important and hard problem of delayed rewards, which I think has been tackled in the ML community separately. But then it's going to be very nice to kind of plug in this short-term reward versus long-term reward formulation together. There's a question by Dima. Can we turn some of these objectives to a constraint within the similar setup? Yes, for sure. That's a very good example. So look, you can solve a multi-objective problem, not just by optimizing all of these together, but you can also view it from a constraint optimization-based solution. So the paper, the CIKM paper I was talking about, that gave one example of a constraint optimization solution. So an example from that paper would be, in that paper, we said that, hey, maybe some product owners don't want to tank relevance after beyond a threshold. So let's say that we want to increase diversity, right? Let's say we want to increase diversity and without hurting, let's say, relevance. So now the constraint could be that, okay, can I just treat this as a constraint optimization problem and say that I'm going to maximize my diversity or fairness with the constraint that the relevance never goes below 0.8. So we can turn some of these problems into constraint optimization problems and then solve them. I'm also going to come back to one paper at the end from Yahoo, which literally views these as like constraint optimization problems and solves it. Cool. So the take-home messages from part 3. So we have looked at, like, there are multiple flavors of approaches available. If you want to make multiple predictions, then you should use multitask learning. If you want to combine multiple things together, then scalarization. Averaging is useful as well. Or, I mean, you can do some richer forms of averaging, including the OWA operators. You can view the same prediction and decision-making problem together in a multi-objective multitask learning setup, and we've looked at multi-objective bandits and multi-objective RL models. So again, like, I mean, it depends on the product maturity you have. I mean, if you don't have a system to deploy these online RL style models, then the first solution of scalarization will give you good enough rewards. Because no matter how you combine things, you're going to end up somewhere on the Pareto front, and then you can make some informed decisions by by intelligently walking on that Pareto front, essentially. So we've also seen that often optimizing for multiple user-centric interaction metrics perform better than directly optimizing those metrics. And one of those biggest takeaways, which I would pitch, is that it need not be a zero-sum game. So we're not claiming that it's always not a zero-sum game, but then like there are formulations wherein you can get gains in all of your stakeholder objectives without hurting some of the other objectives. There's a question from Hari. Are you updating the prediction models based on the observed rewards? Or are you using the scores from? Yeah, that's a good question. Do we, again, up to us, right? In that paper, we are also changing the way the prediction model works. But then if you want to use a fixed prediction model in your contextual bandit formulation, you're free to do so. Or if you want to integrate that together, I mean, in our formulation, let me just quickly go back to exactly what I'm talking about. So in over here, the prediction of reward happens from this ridge regression problem. And this problem, you can fix it or you can solve it together. And in the best extreme, you can do an end-to-end solution. That you can make this as part of the overall learning strategy as well. So we did something in between. We trained a separate prediction model, and then we just updated it regularly. Cool. So with that takeaway, just a time check. So we're kind of okay on time, I think. Oh, no, not really. Okay, so I'm going to switch gears and go to the fourth part of the tutorial. So I'm going to quickly present a brief summary so that if there are some people who have joined now, then you can get a quick summary based on the next two slides.